Hello, everybody, and welcome to OptiWave's webinar, where we're going to discuss the design of a polarization independent waveguide. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your host, Steve Dodds. Before we begin, let's review the layout of today's webinar. So during the presentation, we're going to launch 3 polls like the one you're looking at now. Each poll provides Steve with helpful feedback for guiding the presentation, so your participation in it's greatly appreciated. We're also going to handle questions at any time during the presentation, but via the questions section only. You'll find the questions section in your GoToWebinar control panel. Please note that we're not going to be answering any questions via the raised hand option, so we ask that you please type all your questions into the question sections only. And in the case where you'd like to keep your question completely private, please send it to support@optiwave.com and we'll answer that afterwards. If for some reason we're unable to answer your question during the webinar, we're going to jot it down and reply to you afterwards via email. Also, in the GoToWebinar control panel, you'll notice that we have a handout available. Feel free to download this at any time. And lastly, we'll be recording the webinar and distributing it to all registrants via a download link that you're going to receive in an email tomorrow at this exact same time, so 11 a.m. Eastern Standard Time. In order to access the recording, you'll need to use the same name and email that you used to join the webinar. So without further ado, I'd like to introduce our components product manager and your presenter, Dr. Steve Dodds.
Hello, everyone. I would like to share my screen. Okay, so you can see my screen now. That's good news. What I'd like to do today is to talk about or present a typical example of a problem in the design of optical waveguides. The problem I've selected to show you today is taken from the literature. Oops, spotlight. Okay, now you can see that dot. I believe you can see that red dot. What we're looking at is the transverse plane, and so of an optical waveguide, typical ridge waveguide. It's the transverse plane, so the optical propagation is perpendicular to the screen. It's the light is going away from us or towards us. And waveguides like this typically have 2 modes that are in the fundamental mode pattern. These 2 modes have almost the same shape. They are centered on the core of the waveguide. And the only difference between them is their polarization. You'll get one that comes out where the polarization, that is to say the direction of the electric field, is almost horizontal, exactly horizontal everywhere. That one we call a quasi-TE mode. Another mode with a very similar shape will come out with the same shape, but with the polarization vertical. The electric field will be pointing almost vertical everywhere. If this waveguide is excited with light, linearly polarized light that is horizontal, it will excite the horizontal quasi-TE mode only. And after propagating down the waveguide, at the other end, the light will still be linearly polarized and horizontal. And if it's linearly polarized and vertical, same thing. It would excite only the vertically polarized quasi-TM mode, and after propagation down the waveguide, it will come out the other side vertically polarized again. On the other hand, if the light is linearly polarized, even if it's linearly polarized but polarized at an oblique angle, sort of an inclined angle like this, then this means that light will go into both modes, both the TE and TM mode, both the horizontal and vertical mode. Those modes are very similar, but they do have slightly different propagation constants, which means that after propagation through the waveguide, even if those the light in the vertical and horizontal modes was in phase at the beginning of the waveguide, after propagation of a certain distance, they will be out of phase, so that the light that's coming out of the waveguide isn't linearly polarized anymore. It's going to be some kind of elliptical polarization. So in general, a waveguide like this is not polarization independent. It will change the polarization. That is sometimes undesirable in optical waveguide designs. Sometimes it's desired to have a waveguide that is independent of polarization. The authors of this paper noticed something about waveguides like this. They noticed that those two polarizations, the horizontal and vertical, they do depend, the propagation constants of them do depend on design parameters. In particular, the design parameter, the width of the waveguide, something that's easy to control. An interesting thing happens if you plot the propagation constants of those two modes against the width. I have a slight example here. Here is the various widths, and plotted against this is the modal index of the two modes, the vertical or quasi-TM mode, the horizontal or quasi-TE mode. And what is interesting about this is that for a smaller width, it's the vertical mode that comes out as having a higher modal index. And for a wider width, it's the horizontal mode that comes out with the larger modal index. So since they exchange positions, it stands to reason that they are going to cross somewhere. And that is a sweet spot. If you design a waveguide with this width, it means that those two modes, the vertical and the horizontal ones, have the same propagation constant. Therefore, when we excite the waveguide with an arbitrary polarization at the beginning of the waveguide, if it's arbitrary, yeah, we do have light going into both modes, but even after some distance of propagation, they stay in phase. So the light coming out the other side will have the same polarization as the light going in. And that's therefore a polarization independent waveguide. What I'd like to do today is to show you how you can use OptiWave software to quickly make this plot and solve these modes and find select the parameters of this waveguide to make a polarization independent waveguide. We have an application that is especially convenient for this application. It's called OptiMode, and it's sold with OptiBPM, so I can open it from the OptiBPM product suite. And this is what it looks like when it opens. And we're going to start this simulation right from scratch, right from zero. And to do that, you say, I want to make a new design. And it begins by asking you some questions. It asks for some details about the so-called wafer. This is going to be define the area in which we do our simulation. The width is the x extent of our simulation domain, and 3 microns is going to be wide enough to hold our simulation. The cladding, on the other hand, is the distance above the top of the substrate, and 2 microns will be enough to hold our cladding, and substrate is how deep in the substrate we wish the simulation to go to follow the optical wave. So I can, when I click OK with that, it presents me with a space. This horizontal space is the same as the horizontal, transverse, and vertical. This is the plane in which we create this design. In order to proceed, we do need to define the materials that we're going to work with. There is a refractive index view. This is a layout view, but the same picture is presented showing the refractive index. And so right now in our substrate, we have a refractive index of 1.5. So that's probably some glass substrate. And above in the cladding, we have a refractive index of 1. That's air. So far that's all right. But the example given has materials that are semiconductor materials, so we're going to have to define what they should be. And there's another window that I have here for defining these things. When I open them, there's already several materials defined. For example, here's a silica that it's actually defined with Selmayr coefficients, in fact. But that's not what I need right now. I need some semiconductor materials, so I need to make new ones. So I ask for something new. And the first material that they have is it's got a refractive index of 3.171, I believe, and I need to give that a name, so I'll just call it after its index. So I click Store, and a new material appears in my materials list, and there it is defined. It's a material with index 3.171. And I need another semiconductor material, so I click to create another new one. This one has refractive index 3.45. So I'll create that one and also give it a name. So now I've got the two materials that I need in my list. That's not all I need. I also need to describe generally what sort of shape this is to the designer. And this is a ridge waveguide consisting of layers. We already have a structure in the profiles that's suitable for this. I'll make a new one to show you how that's created. It came up with a name for us. And this is defined as a list of layers. So the first layer is the thickness of it was 0.5 microns. And the material of the first layer is the first semiconductor material. And I add that. And the center layer consisted of the other semiconductor material is 3.45. And then it's got a layer on top, which is, again, the same material again on top. So this is in fact the materials that were given in the example. So now I've got materials defined, and I've got my and the profile, the kind of profile defined. So I can put that away for the time being. And now I have a substrate and a cladding. I just need to add the waveguide in question. And it comes in. It's not really the right size or shape for me. And the reason is that it's not the profile that I've just created. It's another one that was supplied by default. So I'm going to change it to the profile that I just created. And there it appears. It's got the three layers, each half micron in thickness. And if I go to my refractive index view, I've got my 1.71 and 345 1. So now the waveguide appears correct. The substrate is still not the right material. So I'm going to go change that now. This is done from wafer property. Substrate was this material. That's not what I want. I wanted the new material that I made. And I can save this somewhere. Today is Thursday, so I'll call this Thursday. And let's have a look at a refractive index view. And oh yes, this does appear what I want. I've got a substrate, and I've got a substrate, and the substrate and the first layer are the same material, like in this example. There's a higher index core, and then there's the same material again on top, each with thickness 1.5. And so that will, now I have properly defined my structure. Now I'm ready to begin mode solving. When I drop down the mode solving menu, it shows me the different kinds of mode solvers that we have available. We've got one that is based on the beam propagation method, another one that's specifically for anisotropic materials. We have two mode solvers which are specialized to fibers, but you can see that this is not a fiber structure, so these mode solvers are not enabled right now. We have a finite difference solver, and we have a finite element solver. and all of the parameters for these are set in this dialog box. I'm going to use the ADI solver because it's fast and convenient for finding fundamental modes anyway. I want to find two modes because I told you that there will be two modes of the fundamental shape of different polarization. So I'm going to be finding at least two modes all the time because the first two have different polarization. And this is going to be a full vector solving because I do want to resolve the polarizations. Mode solvers have settings. The ADI solver has a complex acceleration parameter. The setting of -2 will make it run fastest, but a larger number there is a little bit more reliable, so I'm going to set it that way. Okay, so I have got a waveguide that appears to have a width of 2, and I'm ready to start solving. And I call the ADI solver. And the solution occurs. It finds the first two modes. That's the second mode, that's the first mode. And these two modes, they both have very similar shape, so we can call them both fundamental modes. But they're different. The first one, the one with the larger modal index, it has two components, and the y component is very small. They're all very small numbers in there. See, it has this consists mostly of EX, so the light is polarized mostly horizontally, and it's identified as a quasi-TE mode. The mode with slightly smaller modal index, it's the opposite situation. The X component of this is very small numbers. It's the Y component of this mode that where all the power is, so the light here is almost completely vertical. It's a quasi-TM mode. And for this example, the width was 2 microns, so we are on the extreme right side of this graph. And as expected, it is the quasi-TE mode that has the higher modal index. We could go do this again. It appears I have closed the design file. I'm going to have to open that again. Get it back. Okay, we can change to a different width. It's simple enough to do this. You simply select the properties of the waveguide, and I change the width from 2 to 1. So now it's much narrower. And let's do the solving again. Once again, I get two modes. of the same shape. This time, the one with the larger modal index is the one that's almost vertical, the quasi-TM, because the x component of that electric field is almost 0. So when I make the width equal to 1, it's the vertical or quasi-TM mode that is the one with the larger modal index. So now I'm on the off the right end of the graph where it's the TE mode. I'm sorry, this time the width is equal to 1, so I'm off the extreme left end of the graph where it is the TM, the vertical mode that has the higher modal index. So you can see it's fairly easy to define these separate points. All you need to do is change the this parameter, the width, and do the solving again. But OptiMode is also able to scan results. We can also ask OptiMode to perform the simulation many times with different widths and record all the results, and even make a graph out of them. We'll be able to make the graph, which is which you can see on the right. So this might be a good time to stop and ask for a second poll, see how you're all doing. Maybe so I'd like to stop for a minute now, hand it back to Brian, and Brian will show you a little poll.
Yeah, so we just got the poll launched. I'll leave it up there for about another 15 or so seconds, and then I'll hand it back to Steve. And if you guys have any questions at this point, this is a good time to ask while we're taking this short little break here. Just type it in the questions section of the GoToWebinar control panel, and we'll have a look at it and then try to get all the answers back to you during the webinar. Okay, I'm going to close the poll now, and back to you, Steve.
Okay, hello again. So I was just about to show how we could get OptiMode to perform this simulation many times with different widths and present the results in table and graph form. So doing this is pretty easy. What you do is have a look at where the width was specified. The field in which the width is specified has a little f of x button, and what that means is that I can specify this instead of just as a number, I can specify it as a parameter. If I click on that little button, it brings up a dialog box which enables me to define parameters. So I could define something called the width. I could set its value to something 2, say. And when I return to the definition of the waveguide box, instead of writing 1, now I'm going to write width. So when I say OK to that, it now gives me whatever the parameter width was as defined. I'll show you how this works. I can access the width independently So now if I go change the width to something else, change this to 1, say, bang, it changes like that. So now that the width is defined as a parameter, it means I'm going to be able to control it out in a scanning simulation. There is another parameter I would like to set. Note that as the width goes from something wide to something narrow, we would also like to change the area in which we do the simulation, that is the window width. And it's possible to create more than one parameter. I can make another one called window width. And I can even define parameters in terms of other parameters. I can say, I want the window width to be whatever the width is, plus another 50%. So multiply the width by 50%. So that would give a value of 1.5. Add that to my list. So now the idea is that I'm going to use the window width to define the actual width of the simulation. That was that width that we set here. Originally we set it to 3. I'm going to set it to this parameter now. So it makes it I have a couple of questions which I'll stop to answer, because they're good questions. Question number 1: how to simulate S-bends in this way? Can it be done efficiently? Well, yes, we do have an option for solving. This works particularly well with the finite element mode solver. It's possible in the finite element mode solver, to solve for modes that are defined on a bent waveguide. And this is done by the method of conformal mapping. What would happen here if you asked for this is that if you select solve for bent modes and you select a radius of curvature, what will happen is the interpretation of this diagram is the transverse plane stays the same, but it's now presumed that instead of propagating directly away in a straight line perpendicular to the plane that you see here, the transverse plane, the propagation starts perpendicular to the plane, but instead of going straight, it goes around a bend, which is located at a radius of curvature away from this centered line, and it goes around the circle like that. And the conformal mapping method is used to simulate this bent propagation. So you could find out what happens if you're connecting to an S-bend or an arc this way by using that option. Question number 2, why am I not exciting with more than 2 modes? Okay, another good question. That's because I assumed that the design given by our from the paper would have been a single mode waveguide. Good question. Let's see what happens if we look for more. I haven't actually done this. And it looks, and it does not find a third mode. So yes, this waveguide has already been designed to be single mode, but that is something that you could investigate. It's as close to single mode as you're going to get because you're not going to be able to eliminate these two polarizations. So at minimum, this is going to be a two-mode waveguide where both polarizations, where we've got a single pattern, a single mode pattern, but two different polarizations. But that question can be investigated simply by asking for more modes and seeing what you get. But yeah, now we know that there aren't more than two, so we won't look for more than two. So I'll set this back to 2. Okay. Okay, another question. If my waveguide is not straight along propagation direction, what should I do? Well, this issue occurs not in mode solvers such as OptiMode. This issue occurs in propagation solvers such as if you're using the beam propagation method or the finite difference time domain method. And those in the beam propagation method in OptiBPM, it is handled automatically. If the waveguide is inclined with respect to the input plane, it does add a phase, modifies the phase of the input mode accordingly to accommodate for the fact that this input waveguide is inclined with respect to the input plane. But for us, for simply the issue of mode solving as it is in OptiMode, this waveguide is presumed perpendicular to the plane. We're only interested in the modes of straight waveguides at the moment, where our conversation is confined to that. All right then. So back to my task, the task at hand. I can't remember if I had changed the wafer or not. Yes, I did. So now the width of the wafer is determined from the parameter. So now, if I change the width, say from 1 to 2, it should change the width of the waveguide, but also increase the simulation area to accommodate for the increase in width. And so it does. It makes it wider, but it also makes the simulation zone wider so that we can contain the wider mode. So that's how parameters work. And once you've got your design parameterized, we have a tool which allows you to scan those parameters, the so-called parameter sweep. So if we go there and we click on parameters, it will present you with a list of the parameters that you have defined so far. I've defined 2 of them. It's the width that is my working parameter. The window width is only there to help with the simulation. So I'm going to select the width as my parameter to scan. It appears in this drop-down list. And here we can define the iteration count. I would like to perform the simulation 6 times. So I put in an iteration count of 6. And what this means now is that if I start a sweep simulation, it will start the simulation, do it 6 times, and it's going to set the width equal to whatever it is I set the values to in this column. We have another little utility which helps to set the parameters in a linear pattern or exponential pattern. I'll set linear. I would like my simulations to start with a width of 1, and I'd like them to finish with a width of 2. So I say OK, and now it presents a schedule for the simulations. It's going to start with our width is equal to 1. It's going to do the second simulation with a width of 1.2, and so on until the width equals 2. And it's going to keep track of all of those. I can also ask it to make a graph. That's done by clicking on the Graphs button. So I add a graph. I need a title for this graph. I'm going to call it Figure 4 because that's actually Figure 4 in the paper that I showed you. And the y-axis of Figure 4 is going to be modal index. So I'll call that modal index. And what I'm plotting against is the parameter width. So I'm going to label the x-axis as width, and I want to plot modal index. So there we are. It's defined a graph. And so now the scan is complete. It's defined. And now when I go to solving, and I select that I want to go to the mode solver, it's now automatically selected the checkbox that we should use. It's all now automatically selected that we should use the sweep script. Instead of just doing the simulation once, we're going to go look at the sweep definitions, and everything else remains the same. We're looking for 2 modes each time. So I click on Run to begin the simulations, and now it does it 6 times, showing the results of each one at a time. And now I'm going to go to the application OptiMode Analyzer. The Analyzer is another application, here it is, that stores simulation results and keeps them all together for later review. The simulation that I just did made a file. It made a file with today's name, Thursday M3A. This is the file that the analyzer opens. This persists. This will always be here. So tomorrow I could come back and open this file and look at these results again. I don't have to run the simulation again. It's a useful thing to have with simulations. Some simulations take a long time to run, so it's nice if you can just come back to review the results. And there's a drop-down box here labeled iteration 1 to iteration 6. What's presented right now is the view is the layout for iteration 1, the first iteration. The last iteration is iteration 6. That's what I get with iteration 6. It also shows what the parameters were for each of these iterations. At iteration 6, the width was 2, and the width of the window was 3. And at iteration 1, the width was 1, and the window width was 1.5. It also shows the modal field for each iteration and each mode. So that's what the picture was of the first iteration. And of the last iteration, I have the opposite polarization in there for each of these modes. The results of everything are also shown in a solver parameters page. This is also iteration specific. So here you can see the modes that were found at iteration 6 together with the parameters at iteration 6. If I switch to another iteration, I get the modes at, this is the modal index at iteration 1, which had width 1. We also see a confinement factor, effective mode area, and full width half maximum for each iteration. And one can see that between iteration 6 and iteration 1, the mode with the higher mode index is changed. But I also asked for a graph, and there it is. This graph can be adorned with a little bit more information. It's possible to put a legend on it. And here we have the width along the bottom. The width is going from 1 to 2. I can even put, let's put some information on this. There's also a tracing utility. You have to tell it which mode you want it to trace. But here it is. Here the width is 1.4. There the width is 1.2. So it's pretty clear that somewhere in between 1.2 and 1.4, I reached my sweet spot where the modal index of these two modes, the two fundamental modes, had the same propagation constant, the same modal index, the same propagation constant. And so what you're looking at right now is you're looking at this graph just on a different scale. So now, having established that the curves do intersect at some point, we could go back and reset our scanning to a narrower range to zero in more exactly on exactly what this magic width is. All right then, that's what I wanted to show you today. I wanted to show you how with OptiWave software you could solve this typical design problem in optical waveguide design. I hope you have enjoyed it, and I would like to ask for any questions. There's time to deal with a few questions before today's web session is over. And it will be possible to send questions after our webinar is finished today. You can send them by email to support@optiwave.com, and I will be happy to answer them for you. So I would like to hand this back to Brian for a few concluding remarks.
So we're just going to launch one more poll here for you guys. And I just wanted to note to everybody that We're going to be at the Photonics North Conference next week. So that's June 7th and 8th. It's here in Ottawa, Canada. So yeah, if you're in the area, feel free to drop by the booth and discuss with us what you're working on and what you'd like to see from our tools in the upcoming years. As Steve said, we're going to leave the webinar running for the next minute to see if anybody has some final questions. If for some reason we didn't answer your questions that you typed into the panel during the webinar, we're just going to handle those afterwards since we get a copy of all of them, and we'll just email you directly. And as Steve said, you can also email us at support@optiwave.com if you want to just send your questions straight into that service. So yeah, we'll leave it for another 30 or so seconds. Doesn't look like there's any last second questions here. So I'd like to thank Steve for the presentation, and I'd like to thank everybody for joining us. Have a good day, everybody.